Tonight's video is about the magnetic field created by a current carrying wire. And hopefully by the end of this video you'll understand how to determine the direction of the magnetic field created by a current carrying wire. First off, we've talked about charges and magnets as if they're completely separate things so far, but turns out they're not. In fact, a moving charge creates a magnetic field. Or more specifically, a changing electric field. So if the charge is moving, its electric field is moving with it. Changing electric field creates a magnetic field. So if we have a wire carrying current, current is the movement of charged particles. So if the charged particles are moving through that wire, they are creating a magnetic field. And it turns out, if you know the direction of the current, the magnetic field is always the same direction. So if you look at this picture, you can imagine current going this way in any situation creates a magnetic field in that direction, shown here. And so if we turned the current around, we'd turn the magnetic field with it. If we flipped the current upward, we'd move the magnetic field accordingly. But luckily, we don't just have to do this in our head because our right hand makes the perfect shape. So if you try this, point your thumb in the direction of the current, that arrow showing current, and if you kind of curl your fingers, you'll notice that the direction your fingers point is the same direction this arrow is pointing here. And in fact, here's an example I like because it puts the two next to each other. If you look at the current carrying wire, current's going up, magnetic field circling around this way. And if you take your right hand and point your thumb in the direction of the current, start to curl your fingers, you'll notice they're pointing the way that circular magnetic field points. And one more time, point our thumb in the direction of the current, fingers curl like the magnetic field. Should try that a couple times. And if the picture still isn't clear to you, you could even Google right hand rule number 2 in Google Images, and you'll find some other good examples of this if you're still not clear. But this is how it works. Thumb in the direction of current, fingers curl in the direction the magnetic field lines point. And so basically, you always get a circular magnetic field around a current carrying wire. And we'll look at how you can use this in this example. Current is flowing through two very long parallel wires, one directed into the page, while the other is coming out of the page. What is the direction of the magnetic field at points A through D? So points A, B, C, and D. Now since there are two wires, and we just looked at a current carrying wire generates a magnetic field, there should be two magnetic fields getting put together. And magnetic fields obey superposition, which means you can add them wherever they collide in space. So let's look at this one as red and this one as blue. So at point A, do the red one first. So I've got my thumb here for the first one. Thumb points out, my fingers curl around, and if you think about the shape they're making at A, they're pointing down. So at point A, the magnetic field from that wire would point down. And if I wanted to check anywhere else, I'd keep kind of the curl going at the bottom. They'd point to the right, and so forth. Okay, so now that we've got that, let's look at drawing that at point A. So at point A, we decided the magnetic field from the first wire, with its current going out of the page, points down. So that's B from the red wire. Now we've got to look at the magnetic field from the wire pointing into the page. So if you point your thumb into the page, curl your hand and keep kind of the curl going until you get them to where A would be. I've got my hand pointing into the page, curl, but then A is over here, kind of where my nose is. Keep that curl going, thumb still pointing into the page. And when I get to where my nose is, I see that the magnetic field is kind of pointing up. That's an awkward one to have to do on camera, but kind of pointing up. I've got my hand pointing into the page. So now let's think about drawing that over here, kind of where my nose is. Field at A. Now I remember from electric fields, the farther you are away from something, the weaker its field gets. And when I get to where my nose is, I see that the magnetic field is kind of pointing up. That's an awkward one to have to do on camera. Should apply to this field as well. Kind of pointing up. So I'll make that one slightly smaller, meaning that the net magnetic field would be a small magnetic field down. So that's our answer at A. And now, why don't you pause and try B by yourself, see what you get. Okay, not going to do this one on camera, because hopefully you got the pattern. Thumb points out of the page for current. Fingers curl, keep them turning until I get to B. For the red wire, my thumb is pointing, or my fingers are pointing up. And if B is right in the middle of those two wires, whatever I get should be the same size. So now I'm going to do fingers pointing, thumb points into the page, fingers curl around until I get to where B would be for that wire. And blue is also pointing up. Should be the same amount, meaning our total or net magnetic field is a big upward vector. Now if I do point C, first for the red wire, thumb points out of the page, fingers curl until I get to C. My curled fingers are pointing up there. B is closer, so its magnetic field line vector will be bigger there, but finger points into the page. When I get to C, pointing down. I've got my hand pointing into the page, curl, and then A is over here, kind of where my nose is. Downward vector. Keep that curl going, thumb still pointing into the page. Also looks like it. And when I get to where my nose is, from the red wire and the blue wire, is kind of pointing up. So first for the red wire, thumb points out. Curl my fingers until I get to D. It's pointing to the right. And then thumb points in. Curl my fingers until I get to D for the blue wire. Pointing left should be the same size. So net, they cancel, and we're left with the 0 vector. That's how you use this. You may want to watch this last 4 minutes or so again. Also, if you're confused, there are lots of examples on YouTube of people doing current carrying wire examples. So if you do search magnetic field from a current carrying wire, you'll find lots of examples. Otherwise, have a good night. See you tomorrow. Be sure you fill out the WSQ form. Wait, that's not actually the end. One more thing. You will occasionally, as in tomorrow, be asked to calculate the strength of a magnetic field from a current carrying wire. To find the direction, you use the right-hand rule number 2 I just showed you. But if you want to know the actual field coming from it, you use this formula. The strength of the magnetic field B equals mu naught I over 2 pi r, where I is the current and r is the distance you are from the wire you're interested in talking about. So distance from wire. We use r because it's a radial distance. If you think about the wire, you'd be talking about moving kind of any point away from it. You could represent with a radius of a circle. Mu naught is a constant. It's 4 times pi times 10 to the negative 7th Tesla meters per amp. That's the equation. You'll get some experience with it tomorrow, but make sure you have it written down.